Swayam Prabha. Digital India. Educated India.
So, in my previous lecture, I was discussing about the reinforced retaining wall or geosynthetic reinforced retaining wall, and I discussed about the failure pattern for extensible and inextensible reinforcement, and then what are the different type of loads under which the wall can be designed. There can be the surcharge load, soil pressure, then the live load. Okay. And today I will discuss that how we can determine the spacing and the length, because as I discussed, what is our things that we will determine? Mainly the spacing and the length. What is the spacing between the reinforcement and what would be the length of the reinforcement? That two things we will determine. Okay. And so this is the retaining wall that we are talking about. So now if I take, say, a small segment in this particular, with half of this in between the retaining wall or in between the retaining wall, the reinforcement. Okay. So, if I take this small segment between this middle of these reinforcement layers. So, as this spacing between two reinforcement layer is SB, and so definitely the thickness of this small segment that we have taken, that is also say SB, because this line is taken the middle of this between these two reinforcement layers. So, this is SB. Clear? So, now that if T is if T allowable, okay, if T allowable is the allowable tensile strength of the reinforcement, then as I mentioned that the stress that this wall is given or this soil is given, because this soil is given the stress on this lateral stress, but here in our previous cases there is a wall, this stress is acting on the wall and wall is supporting those stress or the force, but here who will take this force? So, this force will be taken by the reinforcement itself. So, if this is the small segment and we are assuming that this small segment, the force for this small segment, the force that the small segment will generate, that will be taken by this reinforcement layer, that is within that small segment. Then I can write and that the T allowable is the allowable tensile strength of the reinforcement, which we can determine by dividing the ultimate tensile strength with different factors. So, how I will get the ultimate tensile strength? Either the manufacturer will give you or you can measure that ultimate tensile strength. So, you measure the ultimate tensile strength and from there you apply this factor of safety. So, what are those factor of safety? So, these factor of safety are for installation damage. This is for safety for creep, because of this creep it will lose its strength, reinforcement. Then there is installation damage, because of that it may lose its strength. Then the factor of safety for chemical degradation, then factor of safety for biological degradation. These four factor of safety, if we apply, then if you know the ultimate tensile strength, then you will get the T allowable, or sometimes the T allowable directly given in the design. Now, how I will get this factor of safety for installation damage, factor of safety for creep, factor of safety for chemical degradation, and factor of safety for biological degradation. So, this is the table by which we will get those values, and this is for applicable for walls. For these type of factor of safeties are available for other structures also, like embankment and other structure, but it is for wall. That is why I am giving only the wall factor of safety for installation damage, creep, chemical degradation and biological degradation. So, once I get the T allowable, so that means the amount of, that means this reinforcement, as I mentioned, the reinforcement layer, that tension will develop because it will take the tension. So, this tension will develop, but that developed tension should not be greater than T allowable. Okay. So, if I go back to our this case, this figure, that means how much lateral force will be developed. The lateral force will be developed. The lateral stress is acting in this small segment. So, that stress is, say, lateral stress is, say, sigma h. Okay. Sigma h is the lateral stress. That means sigma h is simple K into sigma V. Okay. K, you can say that is my this if you are designing definitely under active condition. So, it will be Ka into sigma V. Okay. So, that is the lateral stress and thickness is SB. So, the total force that will develop will be equal to tau h into SB, and that force will be taken by that reinforcement layer. So, that should be T allowable. If I utilize the full T allowable, then this is the expression. So, from that I will get that my SV is equal to T allowable divided by sigma h. Clear? So, this way I can get the SV. Now, how I will get the your length? Okay, that is important thing. How I will get the length? Okay. So, length I will get that, as I mentioned, length as your this length as is equal to L R plus L E. Now, L R is very simple. How I will get the L R? You can say L R, because if this is your Z at any depth Z. So, if I say I want to determine the length, this L R. So, here suppose this is my Z. Z is the depth from the top of the reinforcement. So, definitely this will be H minus Z, and this angle is 45 minus 5 by 2. So, this angle will be 45 minus 5 by 2. This is 45 plus 5 by 2, this will be 45 minus 5 by 2. This height is H minus Z. So, this will be simple H minus Z into 45 degree minus 5 by 2, because this angle is how much? This angle is 45 degree minus 5 by 2. Okay. So, now the simple this height LR, I can write that LR is H minus Z into tan 45 degree minus 5 by 2, where H is at any depth, okay, from the top of the reinforced wall. Now, the question is L R. So, now I go back to that. figure. So, LE now. So, LE, so as I mentioned, there will be a pull in the reinforcement, that means the tension will develop in the reinforcement, and from where I will get that resistance between the soil, friction between the soil and the reinforcement. So, that if it is pull is applied here, so I will get the friction here, say both the surface. Okay. So, how I will determine that friction? Say that friction is tau. So, can I write that tau into LE, tau into LE, LE is the length beyond the failure line. So, that will be your tension, resistance or resistance against tension. So, and that is acting both the surface of the reinforcement, because it is horizontal. This side also soil, top is also soil, below is also soil. So, there will be friction between both the surface. So, I can write this will be 2 into tau LE, that is the resistance against the tension, that will be equal to the T allowable. Okay. And T allowable is here sigma. I have already written T allowable is SB into sigma h. So, I can write this is SB into sigma h, because that is equal to T allowable. Clear? So, now if I now write tau, how I can calculate the tau? Tau is simple. If the backfill is C phi soil is there, then this will be C into sigma V at that level into tan delta field. Okay, that is your tau. Now, generally most of the cases in the backfill C is 0. So, if your C is 0, then tau will be simple sigma V tan delta phi. I will calculate the sigma V. This is gamma into Z into tan delta F. F means the field. Okay. So, I can write that this 2 into, or if I put C plus gamma Z tan delta F into LE, that is equal to SB into sigma H. So, I can write LE is equal to, or L capital E, or L capital E, E is equal to SB into sigma H divided by 2 C plus gamma Z into tan delta F. Clear? That way I can determine the LE. Similarly, L0 expression is given SB into sigma H divided by 4 C plus gamma Z tan delta F. Okay. This is 4. So, as I mentioned that LE cannot be less than 1 meter, L0 also cannot be less than 1 meter. So, this is by design methodology, or that this way that we decide the length and the spacing. So, this one is called the internal stability check. So, this is called our internal stability. Okay. And what is external stability? External stability, the same 4 checks that I have discussed. That means the factor of safety against sliding, factor of safety against overturning, then no tension zone, then the bearing capacity. So, those 4 are the external stability checks. Now, these by determine this spacing, and then these are internal stability. Now, this is for say seismic static one. So, now what would be the extension for seismic? What would be the extension for seismic? First, we are talking about the internal stability. So, this is for seismic. So, previous one is under static. So, based on that we decide the length and spacing, then we check whether it is also suitable for seismic or not. Okay? That I will discuss in my example problem. So, it is, as I mentioned, it is a extensible reinforcement we are considering. So, this will be our failure surface or failure zone, extensible. But if it is inextensible, then it will be different thing, but our case we are taking it is extensible. So, it is 45 degree plus 5 by 2 and this one is H. Okay. Now, for here also first we are doing the internal over stability. Internal stability, what we will do? So, this is also a pseudostatic analysis. Okay. So, pseudo first step is the pseudostatic inertial force acting on the unstable internal failure zone. That means here, this is my internal failure zone. Suppose this is your wall. So, reinforced zone is different and failure zone is different. This is my reinforced zone. Okay. But the failure zone is different. This is ground surface. Say. Failure zone is different. So, it is talking about the pseudostatic inertial force acting on the unstable internal failure zone. So, this is the unstable internal failure zone. How I can calculate that? So, that force is P1A, that is equal to AC by G and WA. What is WA? WA is equal to weight of the failure zone. So, that means if this is say L dash, and that you can easily determine because you know this is H, this is 45 degree minus 5 by 2. So, this L dash you can easily determine. That means the WA will be half into H into L dash into gamma, where gamma is the unit weight of the reinforced soil, of the soil in the reinforced zone. Okay, because this is reinforced zone, here it can be gamma R, this is the field zone which is beyond the reinforced zone. So, that can be different, both the cases there can be different soil density. So, this is I should write this is gamma R, which is unit weight of the soil in the reinforced zone, and this is F is the unit weight of the soil in the field, that means the unreinforced zone. Clear? So, this is WA. How I will calculate the AC? So, that means the peak acceleration at the centroid of the reinforced zone, the peak acceleration at the of the reinforced zone can we get AC by G, that is equal to 1.45 minus A max by G into A max by G. What is A max? As you know, that is your peak is the peak horizontal acceleration or ground surface acceleration. So, again remember that A max is the ground surface acceleration, not the base or not the bedrock. So, if you have the PHA for bedrock, then you convert it to ground surface, free surface acceleration or free surface motion by using the ground response analysis. That A max you have to consider. It is not the bedrock. So, that we have discussed during the liquefaction analysis. Here also, retaining wall also, this ground response analysis is required to determine the ground surface acceleration. Clear? So, this is A max, you know that this is the value. So, AC is the peak acceleration at the centroid of the reinforced zone. So, the AC I can get from this equation, and that I can put it here. And one more thing, by using the different codal provision also, you can calculate that your the KH, but our IS code 1893 part 1 2016. Here also they are getting that AH or the KH, which is equal to AH horizontal by, this is divided by G, acceleration, horizontal acceleration divided by G, which is actually the KH or H, that is given by Z by 2 into SA by G divided by R by 1. Okay. So, where your Z is equal to seismic zone factor, that value table I have given, okay, in the liquefaction analysis part. I is the importance factor, importance factor, then your R is the response reduction factor, and SA by G, that is equal to your say design spectra, that SA by G. So, that is equal to design spectral acceleration. So, this is design acceleration coefficient for different soil type. So, these values, the seismic factor, you know, we have the different seismic zone. So, seismic zone factor, importance factor, response reduction factor, design acceleration coefficient for different soil types, those are given in the IS code. The tables are given. So, you can get those values and you can put it here and you will get your H by G. So, that you can calculate and you can consider as Max by G. That you can consider as Max by G. That is your KH, that you can consider, and then that Max H by G you put it here in this equation, then that you will get the AC by G. Okay, that is also one option. And then another option is that I will do, that I will put directly the Max by G, and then I will do the calculation. Okay. So, I will put directly that Max by G and I will do the calculation here. So, that is way we can calculate this pseudostatic inertial force. So, that is acting on the unstable internal failure zone. So, that means this zone. So, this zone it is acting here in this direction, say. Okay. So, that is your PIA. That is only the reinforced failure zone. Next, I will go for the this. Okay. So, once we get the PIA, what is the next step? So, next step will be that I will get the PIA. Next step will be that this you know that how to calculate the T allowable that I have discussed. Now, the next step will be, once I get the PIA, so next step that will be that distribute this PIA to each reinforcement layer. So, distribute that PIA to each reinforcement layer. Such that it is in proportional to its resistance area. That means the area beyond the failure zone. That means the beyond the failure zone. So, that means first you distribute this PIA to each reinforcement layer in proportion to its resistance area. For example, here you can see that here the length is same, say I am providing, but its resistance area is not same, because this is your failure surface. So, that means the lower reinforcement has more resistance area as compared to the top reinforcement. That means the bottommost reinforcement has maximum resistance area. Here you can see, if you consider this triangular failure zone, okay, this bottom resistance reinforcement layer has the maximum resistance area as compared to the top, if I provide the same length of the reinforcement from the top to bottom. So, that means here I have to distribute more reinforcement, more PIA in the bottom reinforcement layer, because here resistance area more. Clear? And remember that these triangular, failure surface I have considered, if I am assume it is the extensible reinforcement. If it is the inextensible, the different failure zone you have to consider, shape of the failure zone, and that I have discussed. So, that means here the bottommost reinforcement layer has maximum resistance area. So, more PIA or the pseudostatic internal force acting due to seismic condition, that will be distributed to in that reinforcement area, and the top reinforcement layer, the lowest PIA value will be given as per this condition, where if your length of the reinforcement is same, and for this particular failure surface, for inextensible case it will be different. Again, if the length is not same of the reinforcement layer, then also this bottom top will be different. So, that means in this case bottom will take the maximum PIA and top will take the lowest PIA, or it will be distributed in this form. Okay. So, now once it will be distributed, then the third one is that the add this dynamic plus static tensile force in the reinforcement layer. Each layer. Okay. And then you check for static, you know that the T developed should not be greater than T allowable. That is for static. When it is static plus seismic, okay, when it is static plus seismic, then you can write that, or I can write that T allowable, if it is static by seismic, then we can write that T allowable should be less than, should not be less than, or I can write this is greater than, T allowable should be greater than your 0.7 times of T develop. That is for static plus seismic. Why? Because as I mentioned, we have to apply that factor of safety for seismic is less than the factor of safety of static. So, that means we are basically reducing the T developed. So, if it is static, whatever the T developed in the reinforcement layer, that should not be greater than T allowable. That is okay. But if in the static plus seismic is force is considered, then the T developed is been reduced by 75%. I mean, it is multiplied by 0.75. That means it is that force is reduced by a multiplication factor of 0.75. In other way, the factor of safety in the seismic is reduced, okay, as compared to the static. So, that means in that case T allowable should be always greater than 0.7 times of T developed, and for static it is T allowable, if I write in the same way, that should be always T full T developed. Full T developed. But here it is 0.7 times of T developed if it is static per seismic. Clear? So, then also check about the LE length also. That means after that, when you consider, because initially LE is designed for under static condition, now if you take static and seismic, then check the amount of LE that is being provided is sufficient or not. That also you have to provide the anchorage length. So, this is for internal stability part. Now, I will discuss about the external stability part. Okay, so in external stability part, here as I mentioned that we have, this is your reinforced zone, this is the backfill zone, okay, this is the H, and this one is say L, length of the reinforcement. Okay. Now, if I consider the forces, suppose this is my reinforced zone and this is H is the height of the wall, and these are the reinforced zone soil. Okay. So, this is reinforced zone. This is reinforced zone. So, what are the forces will act? So, my PA will act for static. Now, for seismic, del PAE will act for seismic, and this weight of the reinforced zone will act, and in inertial force, that P IR, it was IA, this is IR. And obviously, this is the length of the reinforcement. Now, it is not the failure zone, it is or the total reinforced zone. Now, this W, initial W was, it is only the failure zone, failure mass, but here it is the total reinforced zone. Okay, L H, the total L is the length of the reinforcement. If length is same for all the cases. Now, how we will calculate these forces? Now, I can calculate that del PAE by using this equation 0.375 AC by G into gamma. Now, I will calculate gamma field, not gamma reinforced, because this gamma field is the outside the reinforced soil. Now, it is gamma F into H square. Clear? This is your PAE, and similarly, I will calculate this PIR, that is AC by G, acceleration, into mass. Mass is how much? Total area. This total area is your H into L. Now, it is will be reinforced zone. Okay. This is the your mass into acceleration. So, that is your force, inertial force. So, AC by G into this area into the unit weight. Area is H into L into the gamma R here. So, AC gamma R H into L divided by G. H is the height of the reinforced wall. So, remember that here this is for, in case of del PAE it is gamma F, but in case of PIR it is gamma R. That means the reinforced zone, your unit weight. So, gamma R is the unit weight of the reinforced zone, and gamma F is the unit weight of the unreinforced zone, okay, or the your backfill zone. So, now the third thing in the external stability. So, because this is your internal stability, now external stability, third thing, that you add full del PAE, and 50% of PIR to the static forces for external stability check. That means Why I will take 50% of PIR and full PA del PAE? Because it is unlikely that the maximum PAE and PIR will act at the same time. So it will not happen. So that's why it is recommended you take full del PAE and 50% of PIR. And then you add them with the seismic forces, static forces, and then do the external stability checks like your factor of safety for sliding, bearing, then no tension and bearing capacity. Overturning, sliding, no tension and the bearing capacity. So you do the check. And fourth one, again you know that the factor of safety for seismic can be taken greater than equal to of 0.7 times of factor of safety of static. And if you take the 0.7 times, so you know for sliding, if your factor of safety for static is 1.5, so seismic will be 1.15. If the overturning factor of safety is 2 for static, seismic will be 1.5 if I take 0.75. And for bearing, we are directly checking that if that Q allowable is given, so the maximum stress should not be greater than Q allowable. Okay. So these are the design steps for static and the seismic. So for a reinforced retaining wall. So in the next class, I will solve one example problem, and then I will show you how we will take all these design recommendation and we will design a reinforced retaining wall, or as I mentioned, I will do a geotextile reinforced retaining wall under seismic and obviously static condition. Thank you.